but it was very carefully designed to look like accurate code, but in fact was intentionally designed to be malicious. Now, it turns out the attack failed, and for a variety of reasons. First of all, they tried to subvert this trusted repository, but in fact the repository was much stronger and quickly detected the attack. There's also developer review. There's a whole developer review process. They noticed, oh, wait a minute, this is a change, but no one who's authorized to do so was signed off to do it. They looked at the code right away, and it took, I think, seconds for developers to realize, oh, that's an attack. They also had, it turns out, special programming conventions specifically to counter these sorts of things, which in fact wasn't strictly necessary, but it enabled, made it even easier to detect this particular kind of attack. And so someone tried, and we know of at least one case where someone specifically tried. We don't know who it was, at least I certainly don't, and failed quite spectacularly. Now, there have been subversions of Debian and SourceForge, and someone basically managed to subvert the underlying system and gain control of the underlying system. However, it turned out that that one was trivially countered. As soon as that, because open source software is available widely, copies of the source code were also available widely. It turned out it was quite trivial to detect and counter and restore from the many other copies and compare to the many other copies to make sure that although they had gained access, they had not actually made any changes that mattered. Well, if they didn't make any change that mattered from the user's point of view, although of course you don't want this kind of thing to happen, it couldn't have affected the end user. Now, it is true that often malicious code is made to look like unintentional code. Certainly that was the case for the Linux kernel attack. And so it's been argued, well, review can't possibly work because if I make malicious code look like unintentional code, then maybe it'll kind of slip through the review process. Well, it turns out that all the texts to counter unintentional code still apply. And there's a large number of them. There are tool sweats and reviews. If it's a common mistake, there are actually lists, checklists of for people to use that say, hey, look, here are 10 very common mistakes. Make sure you look carefully, especially for those. So if an attacker tries to exploit a common mistake, that's also the very thing that people especially look for, which makes it less likely to survive. Now, an attacker could devise a malicious attack that looked like a not malicious attack and do it in a way that would not be detected by tools that people would be typically using. Okay? Basically, they can look at, well, what tools are you using for review this software? I'll use the same tools and make sure that my attack isn't detected by them. The problem for an attacker, of course, this is not a problem for the defender, but the problem for the attacker is that they don't know the full set of tools that are used to analyze FLOSS. They will know some of them, but they can't know all of them because anyone can download the source code and do private analysis, and many organizations, companies, governments do this. Therefore, even if now I'm going to switch roles, I as an attacker would know at least some of the tools that I as the defender are going to use other tools that may still detect them. So it's a very difficult situation for the attacker to be in. As a defender, I like putting the attacker in a difficult position. There's actually another case, and I'll point this out as well, called the Borland Interbase/Firebird backdoor. This was a program that for many years was a proprietary product. Interbase, it's a database program for Windows. After many years of selling as a proprietary product, the vendor decided to switch over to making it an open source product, which is fine. Now, it turned out that for 7 years, hidden in this product, there had been a trapdoor, a secret way to gain complete control over the system. Basically, it had a password system, but if you typed in the username password, with the username politically, with the password correct, instead of checking the database or anything, it would suddenly give you complete and total control over the system, which is not what any of the users were expecting, let me tell you. It had been hidden in the program for 7 years. No one had noticed this. When it was released as a FLOSS product, within 5 months, that was found. Now, it was not instantaneous. It takes time to suddenly, here's a very large program, start looking at it, okay? But it had been hidden for 7 years, and there's no reason to believe it would have been discovered in the next years after that. When it was a FLOSS program, it was discovered and was countered. Now, I do want to make clear, it is not entirely clear if this particular trapdoor was malicious. It may have been unintentional, although frankly, but it has exactly all the forms of a malicious attack. If it was unintentional, it was a dreadful mistake. But regardless of whether it was intentional or not, it had exactly all the apparent external properties of an intentional subversion. Not countered by being proprietary, it was countered by being open source. Now, let me talk a little bit about malicious attack approaches, particularly the FLOSS versus proprietary. Okay, there are several ways to attack the system, and let me talk about them, because if you are evaluating a program, you want to look to see how they do this. If you are potentially developing an open source software, you want to think about these and put something in place. Okay? Fundamentally, security is very much about trying to figure out what the attacker is trying to accomplish, or at least what you want to accomplish as the defender, and making sure you achieve that. So, first of all, repository distribution system attack. Basically, that trusted repository in your distributors. You want to make sure they're protected. Let's see here. The argument for the traditional proprietary developers is that, well, hey, on our development environments, we're completely disconnected from the internet anyway, so only a few people can attack us anyway. Well, if you completely disconnect from the internet, that does have some advantages in terms of protecting the repository. But frankly, today, most proprietary vendors don't do that anymore. This causes so many losses in terms of efficiency that very, very few people do this except for extremely high-end, high-risk systems. Generally, development's going global. They generally connect to the internet. So frankly, disconnecting is less practical for everyone, be it open source or proprietary. I mean, proprietary development could do this too, but they would incur the same kind of costs and problems the proprietary vendor would trying to do this. The proprietary folks are going to say that my advantage is I can control my distribution. However, the open source folks can pretty easily counter and say, well, yes, but I've got a much easier detection and recovery system via many copies. So basically, if I have a trusted repository, are there other copies elsewhere that are cross-compared, or at least can be cross-compared? Malicious trusted developers. Frankly, open source has a little advantage via review. And they also have another advantage in that you're more likely to know who the developers are. I often see a lot of people getting this wrong, and I find this really, really amusing. If you buy a proprietary product, you typically do not get inside the box the list of every name and social and identifier, say a passport number, of every person who wrote the software. Okay, you simply have no idea who wrote the software in most cases. You have the name of a company, but the name of the company does not tell you anything about who actually developed the software. Typically for open source software, you do know who the developers are. Certainly you know who all the leads are, and the leads who review to decide whether something is accepted into the official product. Frankly, the big advantage here is the open source software is a very major long-term advantage. Multiple reviewers, and the more the better. When you have a lot of people reviewing software, just as with anything else, it tends to be much more likely to find problems. This is the same reason that scientific journals, we do not just allow arbitrary scientists to write a document and then just publish it immediately in a journal. All significant scientific journals have a peer review process of other scientists who look it over and make sure it's accurate. Not because we assume that all scientists are malicious, but simply because it produces a more accurate result, and the same is true here. But there's certainly no evidence that the proprietary software is always better. For the malicious vulnerabilities, countering the repository distribution system attacks, countering malicious trust developers, and